Hello there, and welcome to Just About Ocean, where quiet curiosity meets the deep end of science, and wonder is allowed to take its time. Tonight, we're going to descend into one of the ocean's most haunting mysteries. Not a mystery of what we can see, but what we can hear, because deep beneath the surface, in the lightless zones where pressure could crush submarines like tin cans, something has been making sounds. Sounds so powerful they traveled thousands of miles through water. Sounds that don't match anything in our catalog of the known. Sounds that, decades after we first heard them, still make scientists pause and wonder, what made that? I'd love to know where in the world you're listening from tonight. And what time is it right now where you are? Are you by a coast? Perhaps hearing waves through an open window? Or are you landlocked, miles from the nearest ocean, yet somehow drawn to its mysteries? If this kind of slow burn question is your kind of question, I'd be thankful if you tapped like or subscribed. It helps this quiet signal reach other curious minds drifting through the night, looking for something deeper than the surface allows. So settle in, maybe lie back if you can, and let your thoughts slow down. Let them sink. The way sound sinks through water, traveling farther in the deep than it ever could in air. Tonight, we're listening to the ocean's hidden voice and asking a question that's both simple and profound. If we heard something down there, something unexplained and enormous, would we even know what we were hearing? The ocean has always spoken to us. Of course. Waves breaking on shores, the rush and retreat of tides, the whisper of foam dissolving on sand. These are the ocean's surface conversations, the small talk it makes with the air and the land. But the deeper ocean, the true ocean that comprises most of our planet's living space, speaks in a different language entirely. It speaks in pressure waves, in frequencies that travel through water like ripples, through time itself. And for most of human history, we couldn't hear it at all. That changed during the Cold War, though not for reasons anyone would call peaceful. The United States Navy, locked in an underwater chess game with Soviet submarines, needed to hear what moved beneath the waves. They needed to know where submarines traveled, how they sounded, whether that distant mechanical groan was a propeller or just a whale. So they built SOSUS, the Sound Surveillance System, a network of underwater microphones strung across the ocean floor like a vast secret web. Hydrophones, they're called, listening devices so sensitive they could pick up a submarine's heartbeat from hundreds of miles away. And they did their job. They tracked submarines. They mapped underwater movements. They served their military purpose. But they also did something nobody quite anticipated. They revealed that the ocean was not silent. Not even close. The deep ocean, it turned out, was full of sound. Groans and whistles, rumbles and pulses. The sonic signatures of a world we'd barely begun to understand. Whales. Yes, we knew about whale songs. Those haunting melodies that had captured human imagination. But there were other sounds too. Sounds that didn't fit any known biological pattern. Sounds that came from nowhere and everywhere at once. When the Cold War ended and the Soviet threat diminished, something remarkable happened. The Navy declassified some of their acoustic data and shared it with scientists at NOAA, the National Oceanic and Atmospheric Administration. And those scientists, listening to decades of underwater recordings, began to catalog the unexplained. They gave these sounds names, almost like naming constellations, not because they knew what made them, but because you need to call something by a name before you can study it properly. The most famous of these sounds the one that captured public imagination like no other underwater mystery before or since, was detected on a summer day in 1997. The hydrophones picked it up. Multiple listening stations separated by thousands of miles, all hearing the same thing at slightly different times. A sound rising in frequency, starting low and climbing higher, like someone slowly turning up the pitch on a massive instrument. It lasted for about 1 minute, just 60 seconds of something unknown, broadcasting across an ocean. They called it the Bloop. The name sounds almost comical, doesn't it? Like something from a cartoon, a playful onomatopoeia. But there was nothing comical about what the Bloop represented. When scientists analyzed the sound's characteristics, when they measured its amplitude and frequency and the pattern of its propagation, they realized they were dealing with something extraordinary. This wasn't just loud. This was louder than anything they had on record. Louder than blue whales, the largest animals ever to exist on Earth, whose calls can travel across entire ocean basins. The Bloop was louder than that. Much louder, and it matched a biological profile. The way it rose in frequency, the pattern of its acoustic signature, these were characteristics consistent with sounds made by living things. Marine mammals, specifically. But what marine mammal could be large enough, powerful enough, to produce a sound of that magnitude? Let's pause here and think about what size means in the ocean, because this is where our imaginations start to stretch against the boundaries of what we think is possible. The blue whale, Balaenoptera musculus, reaches lengths of up to 100 feet and can weigh as much as 200 tons. 200 tons. That's the mass of about 30 elephants, or 15 full-grown Tyrannosaurus rex. Blue whales are not just the largest animals alive today. They're the largest animals we know to have ever lived. Period. Larger than any dinosaur, any prehistoric marine reptile, any creature in the fossil record. They are, in a very real sense, the upper limit of what biology has achieved in terms of sheer size. Except, the ocean is very good at hiding things. Consider what we know about the deep sea, that vast realm below 600 feet, where sunlight gives up entirely. We've explored less than 5% of the ocean floor. Less than 5%. We have better maps of Mars than we do of our own ocean depths. The Mariana Trench, deepest point on Earth, reaches down nearly 7 miles. 7 miles of water pressing down with unimaginable force. Down there, the pressure is over 1,000 times greater than at the surface. Over 8 tons per square inch. It would crush a human instantly, collapse a submarine's hull like paper. And yet, life exists there. Not just exists, thrives. Fish with translucent skin and bioluminescent lures. Amphipods the size of dinner plates. Bacterial mats that feed on chemicals seeping from the Earth's crust. An entire ecosystem functioning in eternal darkness, at pressures that seem incompatible with the very concept of life. Every time we send a submersible down, every time we drop a camera into the abyss, we find something new, something that wasn't supposed to exist, that breaks the rules we thought we understood. So when the Bloop was detected, when scientists heard that massive, biological-sounding call, the question wasn't entirely unreasonable. Could there be something down there? Something larger than we've ever documented? Something that lives in the depths, beyond our surveys and our cameras, beyond the range of normal observation? The ocean has surprised us before. The coelacanth, a fish thought to have gone extinct 66 million years ago, was pulled up alive in a fishing net in 1938. just swimming around, unchanged for millions of years, surviving perfectly well while scientists wrote papers about its extinction. The giant squid, Architeuthis ducks, was a legend for centuries. Sea monster stories, sailors' tales, exaggerated nonsense. Surely, until we started finding corpses, washing ashore, until we captured footage of them in their natural habitat, realizing they could reach lengths of over 40 feet, with eyes the size of dinner plates, the largest eyes in the animal kingdom. And then there's the colossal squid, Mesonychotutus hamiltoni, even larger than its giant cousin, living in the deep waters around Antarctica. We've only seen a handful of specimens, most of them dead or dying, pulled up by fishing vessels. We don't know how many exist, how they live, what they do in the depths. We just know they're there, massive and mysterious, occupying an ecological niche we barely understand. So the ocean has precedent for hiding things, large things, things that seem impossible until the moment we finally see them. Could the bloop have been something like that? Some massive, undiscovered creature calling across the deep? The public certainly wanted to believe it. The story spread through the early internet like wildfire. Message boards speculated. Artists drew interpretations. Writers crafted stories about what might be down there. A creature so large it made blue whales look small. Perhaps a relic from prehistoric times. A survivor from when marine reptiles ruled the seas. Perhaps something entirely new, a branch of evolution we hadn't encountered yet. The mystery was tantalizing. Delicious. Exactly the kind of unknown that feeds human imagination. But science moves differently than imagination. Science requires patience, evidence, repeated observation. And in 2005, 8 years after the bloop was first detected, NOAA scientists proposed a different explanation. Not a creature, but ice, specifically an ice quake. When massive ice shelves crack and carve, when icebergs the size of cities break away from Antarctic glaciers, they produce sounds, enormous, low-frequency sounds that travel through water with remarkable efficiency. And when scientists compared recordings of icequakes to the bloop's profile, they found similarities, strong similarities. The mystery, it seemed, was solved. Not a monster, just geology. Just the slow, cold mechanics of a planet where ice breaks and water moves and sound carries farther than we imagine. The bloop was filed away, explained, case closed. Except, that's not quite the end of the story. Because the bloop wasn't alone. There are other sounds in NOAA's catalog of unexplained ocean acoustics. Sounds that don't have neat explanations, that remain stubbornly mysterious despite decades of study. Let me tell you about some of them, because each one deepens the puzzle in its own way. There's Julia, detected in 1999. Julia sounds different from the bloop. Not a rising frequency, but a rapid series of pulses, like a bizarre heartbeat accelerating and then stopping. It was detected by hydrophones near the equator and recorded for about 15 seconds. Analysis suggested it might be biological, but no known animal produces that pattern. The leading explanation now is that it might be ice rubbing against rock. Perhaps an iceberg scraping the seafloor. Possible. Yes. Certain? No. Then there's Upsweep. Upsweep is different from all the others because it wasn't a single event. It's continuous. Or at least, it was. Starting in 1991, hydrophones in the Pacific began detecting a sound that rose in frequency. Paused, rose again, paused. on and on in an endless cycle. It's still going. Actually, though it's gotten quieter over the years, Upsweep has been traced to a location in the Pacific, somewhere near volcanic activity. And most scientists think it's geological, probably related to underwater volcanism. But the pattern is so regular, so rhythmic, that it almost sounds artificial, like a machine humming in the deep, like the ocean's own heartbeat. Their slowdown, recorded in 1997, the same year as the Bloop. Slow down did exactly what its name suggests. Started at a high frequency and gradually decreased over about 7 minutes. 7 minutes of something unknown broadcasting across the Pacific. The sound profile suggested ice again, probably large ice sheets rubbing together or breaking apart. But it's never been definitively confirmed. And there's train, also from 1997, which lasted for nearly 3 minutes and sounded, bizarrely, like a train rising in frequency. The speculation is ice once more, but the sheer variety of these sounds, the different patterns and durations and characteristics, suggests the ocean has many ways of speaking that we're only beginning to understand. What strikes me about these sounds isn't just their mystery, but their timing. Most of them were detected in the 1990 seconds, when SOSUS was still relatively new to the scientific community, when researchers were first learning to listen properly. It's possible, even likely, that the ocean has been making these sounds forever. Icebergs have been calving for millions of years. Underwater volcanoes have been rumbling since the Earth's crust first solidified. But we couldn't hear them. We were deaf to the ocean's language, living on the surface of a planet whose depths were literally incomprehensible to us. That raises an interesting question. What else don't we hear? What other sounds are out there? Too low in frequency for our hydrophones to detect, or too high, or in locations we haven't monitored. The ocean covers 71% of Earth's surface. SOSUS, even at its peak, monitored only a tiny fraction of that. We're sampling the conversation, catching random syllables from a dialogue that spans the entire planet. Imagine trying to understand human language by listening to one street corner in one city for a few hours a day. You'd catch fragments, hints, mysterious phrases that might mean something profound, or might just be someone ordering coffee. That's roughly what we're doing with the ocean. Let's think about sound itself for a moment, because understanding how sound moves through water changes how we think about these mysteries. Sound in air travels at roughly 767 miles per hour, depending on temperature and humidity. Fast, but not that fast. A sound made in New York takes about 4 hours to reach Los Angeles. If it could travel that far, which it can't, because air absorbs and scatters sound quickly. Water is different. Sound moves through water at about 3,400 miles per hour, more than 4 times faster than in air, and it travels farther, much farther, because water is denser and more uniform. Low-frequency sounds, the deep bass notes of the ocean's voice, can travel across entire ocean basins. A whale calling off the coast of California can theoretically be heard by another whale near Hawaii, over 2,000 miles away. The ocean acts as a natural amplifier, a planetary telephone system that's been operating long before humans evolved, long before we even understood that sound was a thing that moved. This has profound implications for how we think about marine life. Whales don't just live in their immediate surroundings. They exist in vast acoustic spaces, territories defined not by what they can see, but by what they can hear. A whale in the Pacific might be aware, through sound alone, of other whales scattered across thousands of square miles. They communicate across distances that would be incomprehensible to land animals. They live in a world where space is measured in echoes and reverberations, where the shape of the seafloor and the temperature of water layers create acoustic highways and dead zones. And if that's true for whales, what might it mean for other creatures? What might live in those acoustic spaces that we can't easily access, can't easily study? The deep ocean is not just physically remote. It's ecologically alien. Creatures down there have evolved in conditions so different from the surface that they might as well be from another planet. No light, extreme pressure, cold that would freeze surface animals, solid, food so scarce that every meal is a rare event, a lucky strike in an endless desert, and yet they've adapted. Deep sea fish have evolved enormous mouths and expandable stomachs, able to eat prey larger than themselves because opportunities are so rare. They've developed bioluminescence, creating their own light through chemical reactions, using it to lure prey, find mates, confuse predators. They've evolved pressure-resistant proteins, cell structures that can function under crushing force. They've solved problems we can barely imagine in ways we're still discovering. Could some of those solutions involve size? Could there be evolutionary advantages to being extremely large in the deep ocean? It's not impossible. Size brings certain benefits, particularly in cold environments where maintaining body temperature is challenging. Larger bodies have better surface area to volume ratios for heat retention. Larger bodies can store more energy, survive longer between meals. Larger bodies are less vulnerable to predation, simply because fewer things can eat you when you're massive. But size also brings challenges. You need more food. You need more oxygen. You need space to move. And the deep ocean, despite its vastness, has structures and limits. And more fundamentally, we can do the math on how large marine mammals can theoretically grow. Body size in aquatic animals is limited by several factors: feeding efficiency, oxygen availability, the mechanical constraints of bone and muscle, the metabolic cost of maintaining that much tissue. Blue whales sit right at the edge of what's biologically possible. They feed on krill, tiny shrimp-like creatures that swarm in massive clouds. Blue whales have evolved a feeding strategy called lunge feeding, accelerating into these clouds with their mouths open, taking in enormous volumes of water and filtering out the krill through baleen plates. It's incredibly efficient, but it requires dense concentrations of prey. You need swarms, vast blooms of krill, to sustain an animal that size. And krill depend on phytoplankton, which depend on sunlight, which means they're concentrated in the upper layers of the ocean, where light penetrates. The deep ocean doesn't have that. No sunlight means no phytoplankton, which means no krill swarms, which means no obvious food source. For a creature larger than a blue whale, could something enormous live down there on a different diet? Possibly. The ocean floor has its own food sources, organic material drifting down from above, carrion, strange ecosystems around hydrothermal vents. But none of those seem likely to support something truly gigantic, something large enough to produce a sound like the bloop. So the biological explanation, while tantalizing, has problems, real problems, that science can't easily ignore. The ice explanation makes more sense from a physics perspective. Ice is massive. Ice sheets in Antarctica can be hundreds of feet thick, containing more frozen water than all the rivers and lakes on Earth combined. When these sheets crack and break, when icebergs carve into the ocean, they release enormous amounts of energy. That energy becomes sound, propagating through water in ways that can seem almost alive. And there's something poetic about that, isn't there? The idea that what we heard, what captured our imagination and made us wonder about hidden monsters, was actually the voice of ice, ancient ice, frozen for millennia, finally breaking free and returning to the ocean. The planet itself speaking, announcing changes we're only beginning to understand. Because icebreaking isn't just icebreaking. It's connected to climate, to warming waters, to currents and weather patterns, and the slow, intricate dance of Earth's climate systems. The bloop might have been telling us something after all, just not what we expected to hear. But let's not close the book entirely on biological explanations, because the ocean is still keeping secrets. There's a phenomenon in marine biology called the deep scattering layer, and it's one of those things that seems impossible until you understand what's actually happening. During World War II, naval sonar operators kept detecting what looked like a false seafloor, a solid layer that appeared about 600 to 1200 feet down. This layer moved, rising toward the surface at night and descending during the day, which was confusing because seafloors generally don't move. Eventually, researchers figured it out. It wasn't a seafloor at all. It was life. Vast schools of fish, squid, krill, and other marine creatures, so dense and so numerous that they reflected sonar signals like solid rock. This layer exists in oceans worldwide, representing what might be the largest migration on Earth. Every night, billions upon billions of creatures rise from the depths to feed in surface waters. Every morning, they descend again, escaping the light and the predators that hunt by sight. This happens every single day, a planetary rhythm of rise and fall, and we only discovered it by accident because we were trying to build better weapons. The deep scattering layer The deep scattering layer reminds us how much biomass the ocean contains. These aren't large creatures, mostly, but collectively, they represent an enormous amount of living tissue. Estimates suggest this layer might contain more biomass than all the fish we actually harvest, all the species we actively study. It's there, moving through the water column every day, largely invisible to human observation. If we can miss something that abundant, that widespread, what else might we miss? What happens in the deeper zones, below, where the scattering layer operates? What exists in the bathypelagic zone, the abyssopelagic zone, those depth ranges where pressure becomes crushing and food becomes scarce? We know some things live there. Sperm whales, for instance, dive down to hunt giant squid, reaching depths of over 6,000 feet and holding their breath for over an hour. That's an extraordinary adaptation, requiring specialized proteins that store oxygen, slow-twitch muscle fibers that don't fatigue, collapsed lungs that avoid nitrogen narcosis, a suite of evolutionary innovations that allow a warm-blooded mammal to function in conditions that would kill most surface animals. And if sperm whales can do it, if they can hunt in the deep and return to the surface, what might live there permanently? What might have evolved to never come up, to spend their entire lives in the pressure and the darkness? There's a creature called the Pacific sleeper shark, Somniosus pacificus, that lives at depths up to 6,000 feet. It grows slowly, lives a long time, potentially over 200 years, and reaches lengths of over 20 feet. We know almost nothing about its behavior, its reproduction, its population numbers. It's out there, swimming in the deep Pacific, mostly indifferent to human observation, and it's just one species. How many others are there? Equally obscure, equally unknown. The ocean has a way of revealing things gradually, reluctantly, like a puzzle that gives up one piece at a time. In 2001, researchers using a deep-sea submersible off the coast of Japan encountered something unexpected. A massive jellyfish, Stygiomedusa gigantea, with a bell over 3 feet wide and arms extending over 30 feet. It drifted through the water like a ghostly parachute, pulsing slowly in the eternal darkness. We'd known about this species from a handful of specimens collected over the previous century, but this was the first time we'd seen one alive, moving in its natural habitat. And it was magnificent. Alien. Improbable. Since then, we've encountered Stygiomedusa a few more times, but only a few. It lives in the deep ocean, the bathypelagic zone, where human observation is rare and difficult. Most of what we know about it comes from those brief encounters. Moments when our paths intersected with something that spends most of its existence beyond our reach. This is how the ocean works. Not revealing everything at once, but offering glimpses, moments of contact between our world and the deep. And each glimpse suggests that what we don't know vastly exceeds what we do know. Let's talk about absence for a moment, because sometimes what we don't find is as interesting as what we do. There are creatures we know existed in the past, but no longer seem to exist, or exist in such small numbers that we can't find them. The Caribbean monk seal, declared extinct in 2008, used to swim in tropical waters, basking on beaches, living alongside humans until we hunted them into oblivion. The last confirmed sighting was in 1952. After that, nothing. Just stories, unconfirmed reports. The ghost of a species that once thrived. Could the ocean hide other extinctions? Could there be species that vanished before we ever documented them? And conversely, could there be species we think are extinct but actually persist in some remote corner of the ocean? The vaquita, a small porpoise endemic to the Gulf of California, is functionally extinct now, with fewer than 10 individuals remaining. In a few years, maybe sooner, we'll likely add it to the list of species that existed once and then didn't. The ocean will be slightly emptier, slightly less diverse, and most people will never notice. But here's the thing about the ocean. It's not static. It changes. Currents shift with seasons and with longer climate cycles. Water temperatures fluctuate. Upwellings bring nutrients from depth, creating temporary oases of productivity. Dead zones form where oxygen depletes, forcing mobile animals to flee or die. The ocean is dynamic, constantly rearranging itself, and creatures respond to those changes. They migrate, adapt, or disappear. So when we talk about whether something could hide in the ocean, whether there could be undiscovered giants lurking in the deep, we're really asking several questions at once. Could something that size exist biologically? Could the environment support it? And could it have avoided detection for this long? The biological question has its constraints, as we discussed. The environmental question is trickier. The deep ocean is not uniform. There are trenches and seamounts, ridges and abyssal plains. There are areas of unusual productivity, places where currents bring nutrients from depth or where underwater mountains force deep water upward. These places can support more life than the surrounding desert of the abyssal deep. If something large existed, it might concentrate in those areas, following food sources that shift and change with oceanographic patterns. And the detection question is perhaps the most interesting, because it touches on how we actually study the ocean. Most of our knowledge comes from a few methods: ships with sonar, satellites measuring surface temperature and color, underwater vehicles exploring specific sites, fishing nets pulling up whatever happens to be in their path. Each method has limitations. Sonar shows structure but not detail. Satellites only see the surface. Submersibles can explore thoroughly, but only in small areas. Fishing nets catch what exists in the upper water column, missing everything that lives deeper or is smart enough to avoid nets. We're sampling, essentially, taking small sips from an enormous cup, trying to understand the whole from fragments. And the ocean is very good at hiding things from fragmentary observation. It's dark, it's vast, it's three-dimensional in a way that makes mapping incredibly complex. On land, we can survey from above, use aerial photography, track animals with satellites. In the ocean, most of those tools don't work. Light doesn't penetrate. Satellites can't see through water. Tracking devices need to surface to transmit data. We're working blind, or nearly so, feeling our way through the dark. Does that mean there could be something large we've missed? Something that produces sounds we can't explain? I think the honest answer is probably not, but we can't be completely certain. The constraints on size seem real. The food web doesn't obviously support something larger than blue whales. The physics of how bodies work, how metabolism functions, how energy gets converted and used, all suggest there are limits. Hard limits, not arbitrary ones. But the ocean has surprised us before. Not with creatures larger than blue whales, but with creatures that shouldn't exist at all according to our prior assumptions. Life at hydrothermal vents, surviving on chemistry instead of sunlight. Life in the deepest trenches, functioning at pressures that should denature proteins. Life frozen in Antarctic ice, metabolizing so slowly it barely counts as alive by our usual standards. Each discovery rewrites some small part of what we thought was possible. So, perhaps the question isn't whether there's a giant monster in the deep, but what else is down there that we haven't imagined yet? What forms of life, what adaptations, what strange solutions to the problem of existence in the deep ocean? Because the ocean doesn't need monsters to be mysterious. It just needs to be itself. Vast, dark, deep, and largely unexplored. Let me tell you about an expedition that happened in 2019, because it illustrates how exploration works in the modern era and what we're still finding. Victor Vescovo, a private explorer and former naval officer, descended to the deepest part of the Mariana Trench, a place called Challenger Deep, over 36,000 feet below the surface. He went down in a specially designed submersible, a capsule of titanium built to withstand pressures that would crush any ordinary vessel. The descent took hours, dropping through layers of water that changed from blue to black, from teeming with life to seemingly empty, from familiar to utterly alien. At the bottom, he found life. A snailfish, translucent and small, swimming along the seafloor. Amphipods, those oversized crustaceans, scavenging whatever organic matter drifts down from above. And he found something else too. Plastic. A plastic bag, drifting in the deepest place on Earth. Proof that human activity reaches even there, even to the most remote corner of the ocean we know about. That discovery was sobering, But it wasn't really surprising. We found plastic everywhere in the ocean. From surface waters to the abyssal plains, microplastics in the guts of fish, in the stomachs of seabirds, accumulating in food webs we're only beginning to map. We've changed the ocean, sometimes in ways we notice, often in ways we don't. And those changes affect sound, too. Ships produce noise. Not just the noise of engines and propellers, but sound that radiates through the water, filling acoustic spaces that used to be quiet. Commercial shipping has increased dramatically over the past century, and with it, ocean noise has risen. Studies show that ambient noise levels in some parts of the ocean have increased by as much as 30 decibels since the 1960 seconds. 30 decibels is significant. It's roughly the difference between a library and a busy street. And for creatures that depend on sound to navigate, communicate, and hunt, that increase is not trivial. Whales, particularly baleen whales, like blues and fins, communicate over long distances using low-frequency calls. But those frequencies overlap with ship noise. It's possible that whales today can't hear each other as well as they could a century ago, that their communication range has been reduced by human activity. We've literally made the ocean louder, and we don't fully understand what that means for the creatures that live there. Could that noise affect our ability to detect unexplained sounds? Absolutely. The ocean's acoustic environment has changed, and with it, what we can hear clearly. Some sounds might be masked now, hidden beneath the constant rumble of shipping and industry. Others might be distorted, arriving at hydrophones in ways that make them harder to analyze. We're not just listening to the ocean, we're listening to a version of the ocean that's been remixed by human presence. That's not to say the bloop and the other unexplained sounds are being obscured. Those sounds were loud enough to cut through background noise. But it does mean the ocean we're listening to today is different from the ocean of 50 years ago, and very different from the ocean of 500 or 5,000 years ago. We're observing a system in transition, trying to understand baseline behaviors while simultaneously changing the baseline. There's an idea in ecology called shifting baseline syndrome, and it's relevant here. Each generation of scientists accepts, as normal, the conditions they first observe. If you start studying the ocean in 1990, then 1990 becomes your baseline. You compare everything to that year, those conditions. But 1990 wasn't pristine. The ocean in 1990 had already been altered by centuries of fishing, decades of pollution, years of climate change. And scientists who started in 1960 had a different baseline, one that seemed normal to them, but would have been strange to someone from 1900, and so on, back through time. Each generation measuring change against a reference point that was itself already changed. What does the ocean sound like in its natural state? We don't really know. We have no recordings from before human industrial activity. We can guess, extrapolate, imagine, but we can't know. The ocean's acoustic signature has been altered, and we're listening to something that's already been modified by our presence. This matters when we think about mysteries like the bloop, because it reminds us that the ocean is not a fixed thing. It's dynamic, responsive, constantly adjusting to inputs from climate, chemistry, biology, and human activity. The sounds we hear are part of that dynamic system. Some are ancient, fundamental, the ocean doing what it's always done. Others are new, artifacts of change, signals of stress or transformation. Distinguishing between them requires patience and humility. Let's return to ice for a moment, because ice is not just an explanation for mysterious sounds. It's a character in its own right, a major player in the ocean's story. Antarctic ice contains about 90% of Earth's fresh water, locked in sheets that can be over 2 miles thick. That ice has been there for millions of years, accumulating slowly, compressing into layers that record ancient climates, like tree rings, record seasons. When ice cores are drilled and analyzed, scientists can read the atmosphere's composition from hundreds of thousands of years ago, see how temperatures changed, how carbon dioxide levels fluctuated, how the planet breathed in and out through ice ages and warming periods. But that ice is not eternal. It's melting, not uniformly, not everywhere, but measurably, significantly. Glaciers that were stable for millennia are retreating. Ice shelves that buttressed larger sheets are breaking apart, and each time a major piece breaks free, it produces sound. Icequakes, as NOAA calls them, releasing energy that's been stored as stress in frozen water for centuries or millennia. So the bloop, if it was indeed an icequake, wasn't just ice breaking. It was a small moment in a much larger story. A story about planetary change, about systems reaching tipping points, about the Earth adjusting to new energy balances. That's not as immediately exciting as discovering a new species of giant creature. But it might be more important, because ice breaking tells us something about where we are as a planet, where we're going, what we might lose. Antarctic ice shelves act as plugs, holding back the glaciers behind them. When shelves collapse, glaciers speed up, flowing faster toward the ocean, contributing more to sea level rise. The Larsen B ice shelf collapsed in 2002, disintegrating over a few weeks after being stable for over 10,000 years. It produced sounds, undoubtedly, groans and cracks, and the roar of ice sliding into water. We might have missed some of those sounds, or attributed them to other causes. But they happened, part of the ongoing transformation of the planet's cryosphere. There's a kind of violence in that transformation, though not intentional, not malicious, just physics and chemistry operating at scale. Ice that formed when humans were still learning to control fire is now returning to liquid water, joining the ocean that it left thousands of years ago, and the ocean receives it, warming slightly, rising slowly, changing in ways that will reshape coastlines and weather patterns, and the distribution of life itself. When I think about the bloop now, knowing what we know, or think we know, I find myself not disappointed by the explanation, but strangely moved by it. We wanted a monster, yes. We wanted something that confirmed our suspicions that the ocean still held large, dramatic secrets. But what we got instead was a reminder that the ocean is connected to everything else, that ice and water and sound and temperature and biology and human activity all intersect in complex ways, that the ocean speaks in many voices, and learning to understand those voices requires us to listen carefully, patiently, without rushing to the answers we find most exciting. Are there still unexplained sounds in the ocean? Almost certainly. The ocean is too vast, too variable, too rich, with processes for us to have catalogued everything. New sounds will be detected as our listening networks improve, as we deploy more hydrophones in more locations, as we get better at filtering signal from noise. Some will have obvious explanations. Others will puzzle us for years before someone makes the right connection, proposes the right mechanism, finds the evidence that makes everything click into place. And will any of them be biological? Possibly. We're still discovering new species of whales, new populations, in unexpected places. In 2003, Japanese researchers identified a new species of baleen whale, Omura's whale, that had been confused with Bride's whales for decades. It wasn't a hidden monster, just a case of mistaken identity, but it showed that even large, visible animals can escape proper classification. And if that's true for whales that surface to breathe, what might be true for creatures that never surface, that live their entire lives in zones we rarely access? There's also the question of deep-sea gigantism, a real phenomenon where creatures that live at depth tend to grow larger than their shallow water relatives. Giant isopods, for instance, are related to the pillbugs you might find in your garden, but they grow to over a foot long. Giant squid and colossal squid, as we mentioned earlier, giant amphipods, giant sea spiders, specimens that would look monstrous if we encountered them on land, but are perfectly adapted to life at depth. The mechanisms behind deep-sea gigantism aren't fully understood. It might be related to cold temperatures, which slow metabolism and allow for longer lifespans and continued growth. It might be about pressure, about oxygen efficiency, about the advantages of being large when food is scarce. Or it might be multiple factors working together, a suite of environmental conditions that favor size in ways that don't apply to shallow water. Does this mean there could be truly giant creatures in the deep, larger than what we've found so far? The mathematical constraints still apply. You need food. You need oxygen. You need reproductive success. But within those constraints, there might be room for surprises. Not blue whale-sized surprises, probably, but significant ones. A squid species larger than the colossal squid. A fish that reaches sizes we haven't documented. Something that occupies a niche we haven't fully mapped. The ocean's food webs are complex, much more so than terrestrial systems in some ways. On land, energy flows in relatively straightforward paths. Sunlight to plants to herbivores to predators. But in the ocean, you have multiple layers, both literal and figurative. Surface productivity feeds the upper water column. Dying organisms sink, carrying nutrients and energy downward in what's called marine snow. Aggregations of this organic matter drift through the water like underwater blizzards, feeding creatures at various depths. Some of it reaches the seafloor, where scavengers and bacteria break it down, recycling nutrients that may eventually return to surface waters through upwelling currents. This vertical dimension creates opportunities for creatures to specialize in ways that don't exist on land. You can be a filter feeder, straining microscopic particles from water. You can be a scavenger, waiting for carrion to fall from above. You can be a predator hunting in the deep scattering layer. You can be a chemosynthetic organism, feeding on chemicals from volcanic vents, independent of sunlight entirely. Each strategy opens up ecological space. So when we ask whether the ocean could hide something large, something that makes unexplained sounds, we're really asking whether there's ecological space for such a creature. Space in the physical sense, yes, but more importantly, space in the energy budget of the ecosystem. Is there enough food? Is there a niche that hasn't been filled? Is there a way of living that would allow something large to persist without us noticing? The evidence suggests probably not. We've mapped marine food webs fairly thoroughly, at least in their broad outlines. We understand where energy enters the system, how it flows, where it accumulates. Large predators need large prey populations. which need even larger populations of smaller organisms, all the way down to primary producers. A hidden giant would need a hidden food web, something operating outside our observations. And that seems increasingly unlikely the more we learn. But I want to be careful not to close the door entirely on mystery, because that would be dishonest. Science is provisional. It's based on the best available evidence, interpreted through frameworks that themselves evolve as we learn more. What seems impossible today might be revealed as merely improbable tomorrow. What we think we understand might turn out to be incomplete, missing some crucial piece that changes everything. Consider bioluminescence. We now know it's incredibly common in the ocean, especially at depth. Most creatures in the mesopelagic and bathypelagic zones produce light in some way. But we didn't always know this. Early ocean scientists, working with nets and dead specimens, had no idea that these creatures glowed in life. It was only when we started using submersibles, observing creatures in their natural habitat, that we realized the deep ocean is not uniformly dark. It's full of light, dim and flickering, produced by living things for purposes we're still working to understand. That discovery changed how we think about deep-sea ecology. It revealed communication systems, hunting strategies, defensive mechanisms that were invisible to earlier generations. And it happened recently. Within living memory, the first observations of bioluminescence in living deep-sea creatures were made in the 1,960 seconds and 70 seconds. Before that, we were literally in the dark about this fundamental aspect of deep-sea life. What else might we be missing? What other fundamental aspects of ocean ecology remain hidden because we haven't developed the right tools to observe them, or haven't looked in the right places, or haven't asked the right questions? There's a concept in physics called dark matter. It's matter that doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation in any way we can detect directly. We only know it exists because of its gravitational effects on visible matter. Galaxies rotate in ways that don't make sense unless there's much more mass present than we can see. That unseen mass is dark matter, and it apparently makes up about 85% of all matter in the universe. 85%. We live in a universe that's mostly made of something we can't observe directly. The ocean doesn't have dark matter, but it has something analogous. Processes and organisms that leave subtle traces that affect the systems around them in ways we're only beginning to measure. The microbial life of the ocean, for instance, is staggeringly diverse and abundant. Bacteria and archaea and viruses, numbering in the billions per liter of seawater, conducting chemical reactions that drive nutrient cycles, processing organic matter, producing oxygen, consuming carbon dioxide. These organisms are invisible to casual observation, but they're fundamental to how the ocean works. They're the engine that powers everything else. For most of human history, we had no idea they existed. Even now, we've only catalogued a fraction of marine microbial diversity. Most species can't be cultured in laboratories, can't be studied using traditional methods. We detect them through genetic sequencing, finding DNA in water samples, and trying to figure out what organisms produced it, how they live, what they do. It's detective work, piecing together function from fragments of information. And this invisible world affects things we care about. Ocean acidification, for instance, the process by which atmospheric carbon dioxide dissolves in seawater and lowers pH, directly impacts calcifying organisms like corals and shellfish, but it also affects microbial communities, changing which species thrive and which decline. And those changes ripple upward through food webs in ways we're only beginning to trace. The ocean's invisible majority is responding to environmental changes, and their responses will shape the ocean's future in ways we can't fully predict. I bring this up not to draw a direct parallel to unexplained sounds, but to illustrate how much of the ocean's functioning happens below the threshold of easy observation. We're getting better at seeing the invisible, at detecting the subtle, at measuring the small, but there's still a gap between what we can observe and what actually happens. And in that gap, mysteries persist. Let's talk about one more creature before we wind down, because it represents both what we've learned and what we still don't know. The giant oarfish, Regalekus glesnae, is the longest bony fish in the world, reaching confirmed lengths of over 30 feet, with unconfirmed reports of specimens up to 50 feet. It's a silvery, ribbon-like creature that lives in the mesopelagic zone, between 600 and 3,000 feet deep. It's rarely seen alive. Most of what we know comes from specimens that wash ashore, dead or dying, or occasional encounters with submersibles. For centuries, oarfish were thought to be sea serpents. When one washed up on a beach, people saw its long, sinuous body, its bright red dorsal fin running the length of its back, its small head and large eyes, and thought, monster. Stories spread. Legends grew. The oarfish became part of maritime mythology, a creature that bridged the gap between reality and imagination. Now we know they're real fish, not monsters, just unusual. They swim vertically in the water column, head up, using their dorsal fin to undulate forward. They feed on small fish and squid and krill, filtering them from the water. They're probably solitary, probably slow-moving, probably not aggressive toward anything larger than their prey. They live their lives in the deep ocean, occasionally coming near the surface when sick or injured, and mostly dying without ever encountering humans. The oarfish reminds me that the ocean's mysteries often turn out to be stranger than the monsters we imagined. We wanted sea serpents, and we got a fish that swims standing up. We wanted creatures that defy biology, and we got creatures that defy our assumptions about what fish can be. The ocean is full of improbable solutions to the problem of existence, adaptations that seem fantastical until we understand the environmental pressures that shaped them. And maybe that's the real lesson of the bloop and the other unexplained sounds. They capture our imagination because they represent the unknown, the possibility that the ocean still holds dramatic secrets. But the actual secrets the ocean holds might be more subtle, more interesting, more profound than simple monsters. The secret might be how ice sheets record climate history and announce their collapse through sound. The secret might be how microbial communities reshape ocean chemistry. The secret might be how creatures at depth have evolved solutions to problems we barely understand. The ocean speaks, yes, in groans and whistles, in rumbles and pulses. Some of those sounds we've explained, others remain mysterious, at least for now. But every sound is part of a larger conversation, a dialogue between ice and water, between geology and biology, between the deep and the surface, between past and present and future. We're learning to listen better. Our hydrophone networks are expanding. Our analytical tools are improving. We're developing artificial intelligence systems that can sort through vast amounts of acoustic data, identifying patterns humans might miss, flagging anomalies for further study. We're getting better at distinguishing biological sounds from geological ones, at tracking individual whales across ocean basins, at understanding how sound propagates through water under different conditions. And we're finding new things, not monsters, usually, but genuine discoveries, new whale songs, new vocal behaviors, new patterns of migration and communication, evidence of earthquakes we didn't know were happening, ice events we weren't monitoring. The ocean is revealing itself slowly, in the way oceans do, giving up information grudgingly but consistently. If there are more sounds like the bloop waiting to be discovered, we'll probably find them. And when we do, we'll go through the same process. Initial excitement, wild speculation, careful analysis, gradual understanding. Some sounds will have obvious explanations. Others will take years to figure out. And a few might remain mysterious. Reminders that the ocean is still larger than our ability to comprehend it fully. But here's what I think is important. The mystery itself is not the point. Or rather, it's not the only point. The mystery is the invitation. It's what draws us in, what makes us curious, what motivates us to look deeper and listen more carefully. But what we find when we accept that invitation, what we learn in the process of investigation, that's where the real value lies. We wanted to know what made the bloop. We learned about ice dynamics, about how climate change affects polar regions, about acoustic propagation through seawater. We learned about the limitations of our monitoring systems, about how sound travels differently at different depths, about the sheer scale of what we're trying to observe. We learned about our own tendency to anthropomorphize the unknown, to see intention and agency where there might be only physics and chemistry. And we learned that the ocean is not holding out on us. It's not keeping secrets deliberately. It's just being itself. Vast and complex, and operating on scales that don't naturally align with human perception. We evolved on land, in air, where sight is the dominant sense and where space is essentially two-dimensional. The ocean is different. It's three-dimensional, dark, dominated by sound and chemical signals, structured by density and temperature and pressure. Understanding it requires us to think differently, to develop intuitions that don't come naturally to terrestrial creatures. That's hard work. It requires patience, funding, technological development, collaboration across disciplines. It requires accepting that we won't know everything immediately, that some questions will take decades to answer, that some answers will lead to new questions we hadn't thought to ask. But it's worth doing, not because the ocean owes us answers, but because understanding the ocean means understanding our planet. The ocean regulates climate, produces oxygen, absorbs carbon dioxide, feeds billions of people, drives weather patterns, shapes coastlines. It's not separate from human concerns. It's central to them. And the more we understand about how it works, the better equipped we are to make decisions about how we interact with it. The unexplained sounds are part of that larger project. They're data points, signals from a system we're trying to understand. Some will turn out to be important. Others will be curiosities, interesting, but not central to any major process. But all of them contribute to our growing knowledge of the ocean's acoustic environment, which contributes to our understanding of ocean dynamics, which contributes to our ability to predict and respond to changes. I think about a researcher sitting at a computer somewhere, headphones on, listening to recordings from a hydrophone deployed thousands of miles away. Hour after hour of ocean sound. Most of it is background noise, the constant hiss and rumble of wind and waves and rain. But occasionally, something unusual, a sound that doesn't fit the pattern, and the researcher marks it, notes the time and location, starts the process of analysis. What made that sound? Where did it come from? Is it biological, geological, artificial? Does it match any known signature? Or is it something new? That work is not glamorous. It's tedious, detail-oriented, often frustrating. Most anomalies turn out to be known phenomena, just recorded from a new angle or under unusual conditions. But occasionally, rarely, there's something genuinely unexpected. A new whale song, an ice quake from an ice shelf nobody was monitoring closely. A sound that reveals something about how the ocean works that we hadn't appreciated before. Those moments justify the tedious hours. They're why scientists do this work, why funding agencies support it, why we build hydrophone networks and maintain them and process their data year after year. Because the ocean is worth understanding, and understanding requires attention, sustained attention over long periods. The bloop got attention because it was dramatic, loud, seemingly inexplicable. It captured public imagination in a way that most ocean research doesn't. And that's fine, that's useful, even if the bloop made people curious about the ocean, made them wonder what else is out there, made them think about how much we still don't know, then it served a purpose beyond its immediate acoustic properties. But I hope it also makes people appreciate the less dramatic aspects of ocean science. The patient accumulation of data, the slow construction of understanding, the recognition that nature doesn't organize itself around human narratives, doesn't provide neat resolutions, doesn't always deliver the answers we want in the form we want them. The ocean contains mysteries, yes, but it also contains knowable things, understandable processes, patterns that reveal themselves to careful observation. And sometimes the most profound discoveries are not the ones that make headlines, but the ones that quietly reshape how we understand the world. There's a kind of humility required to study the ocean properly. You have to accept that you're small and the ocean is large, that your lifespan is brief, and the ocean's processes operate on timescales from microseconds to millennia, that your perspective is limited and the ocean is three-dimensional, extending from sun-bright shallows to pitch-black abysses, from tropical warmth to polar cold, from coastlines to the open sea. You have to accept that you might spend your entire career studying one small aspect of one small region and still not understand it completely, that the questions you answer might lead to more questions, that certainty is rare and provisional, that the ocean will continue to surprise you no matter how much you learn. But there's a joy in that, too, a satisfaction in knowing that there's always more to discover. That curiosity can be sustained indefinitely. That wonder is not something you outgrow, but something you cultivate. The ocean offers that, not just through dramatic mysteries like the bloop, but through every small discovery, every unexpected observation, every moment when the data reveals something you hadn't anticipated. So where does that leave us? Here at the end of our journey tonight, we started with a sound, 1 minute of acoustic anomaly, recorded in 1997. We wanted to know what made it, and the answer, the best answer we have, is ice. Ancient ice breaking free, returning to the ocean, announcing changes we're still trying to understand. It's not the monster we might have hoped for, but it's real and significant and connected to systems that matter. And in a way, that makes it more important than any monster could be. Because monsters are stories we tell ourselves about the unknown. But ice is physical reality, responding to energy inputs we've changed through our own activities. Ice doesn't care about our narratives. It just responds to temperature and pressure and time. And when it breaks, it speaks. Whether we're listening or not, the ocean is still making sounds we don't understand. It will keep making them. Some we'll figure out quickly. Others will take time. And some might remain mysterious for decades, waiting for the right insight, the right data, the right question to make them comprehensible. That's okay. Mystery is not a failure of understanding. It's a natural state when you're dealing with something as vast and complex as the ocean. And the process of moving from mystery to understanding is where science happens, where knowledge grows, where we become slightly more capable of comprehending the planet we live on. If you take away anything from our time together tonight, it connects us to processes happening in the deep, processes that affect everything from climate to fish populations to the shape of coastlines. And it reminds us that the Earth is still an active, dynamic system, still creating, still changing, still speaking in voices we're only beginning to understand. The bloop was one voice in that larger chorus. Not a monster, but not less interesting for being explained. Just part of the ongoing conversation between ice and water, between physics and chemistry, between the solid and liquid phases of our planet's hydrosphere. And we were fortunate enough to hear it, to record it, to wonder about it, and eventually to understand it. At least in part. There will be more bloops, more unexplained sounds that capture our imagination and challenge our understanding. And we'll investigate them carefully and patiently, using the best tools we have. Most will turn out to be known phenomena in new contexts. A few might be genuinely new discoveries, but all of them will contribute to our growing acoustic map of the ocean, our understanding of the largest habitat on Earth. So rest now. Let these thoughts settle, like marine snow drifting through dark water. Let the mystery and the explanation coexist in your mind, because both are true in their own ways. The ocean holds wonders, yes, but the wonders are not always what we expect. Sometimes they're stranger, sometimes they're subtler, sometimes they're more important than the dramatic monsters we imagined. Sleep well, ocean dreamer, and know that below the surface, in the vast dark deep, the ocean continues its ancient conversation. Ice groans and cracks. Whales call across impossible distances. Earthquakes rumble through seamounts. And somewhere, perhaps, a sound is being made right now that we've never heard before, that we won't hear until months or years from now, when someone reviews a recording and pauses, listens again, and wonders, what made that? The ocean keeps its mysteries close, but yields them slowly to those who listen with patience and care. And in that slow yielding, in that patient listening, we find not just answers, but connection. Connection to processes larger than ourselves, to a planet still revealing itself, to depths both literal and metaphorical that invite us to wonder. Thank you for drifting with me through these dark waters tonight. Thank you for your curiosity, your patience, your willingness to sit with questions that don't have simple answers. The ocean is richer for being observed, and we are richer for observing it. May your dreams tonight be deep and strange and full of sounds that echo from places you've never been but somehow recognize. Until next time, when we'll dive into another mystery, another question, another invitation from the ocean to come closer and listen carefully. Sleep well. The waves continue their eternal rhythm. The deep continues its patient work. And somewhere in the vast blue heart of our planet, Something unknown is moving through water, living its life, making sounds we might someday hear and understand. Rest now. The ocean is speaking, and we're learning its language, one sound at a time.